Howdy. Okay, we're going to take you through the exercise of how to differentiate an expression implicitly. So what does that mean to say that we're doing implicit differentiation? Well, ordinarily, we write expressions in the form of y is a function of x. But very often, we'll have an expression where the function is itself dependent on y. And in order to differentiate that expression, we have to address that functional dependency on what is ordinarily considered the dependent variable, in this case, the variable y. And you can see that in this expression that's written in line 1 that says x squared plus 3x plus xy is equal to 5. So if we consider the fact that what's on the left-hand side is the functional dependency and what's on the right-hand side is the independent functionality, then you can see that both x and y appear on the left-hand side. And so the equation is by itself implicitly dependent on both the dependent and the independent variables. Now, this is an easy example because you can look at this and you can say, well, I can algebraically manipulate this equation so that I have my independent function on the right-hand side, all of my independent variables on the right-hand side, leaving only dependent variable on the left-hand side, and then differentiate explicitly, as we would commonly do where we say dy equals dx, and then differentiate the right-hand side. But again, this is an easy expression where it's very clear that we have that ability to explicitly write the dependent variable y as a function of only the independent variable x. Oftentimes, equations don't exist like that in nature. You necessarily will have dependency of the dependent function within the expression itself. And so to differentiate that, we have to apply what is called implicit differentiation. So what we'll do is we'll first differentiate the expression implicitly, demonstrating that technique. We'll then actually differentiate the expression explicitly, where again, we move all of these variables, the independent variables, to the right-hand side of the equation so that we have our expression written in the usual form of y equals fx, and then differentiate it explicitly as we're familiar with doing already. But the two expressions should essentially be the same. And so in the last part, C, we'll compare the two differentiation techniques to prove that, in fact, they are the same. And so the differentiation implicitly is, by all means, an appropriate technique to differentiate an implicitly based function. Okay, so first of all, to differentiate implicitly, what does that mean? So what we're going to do is we're going to write our differential expression for both the left and right hand side of the equations. So what that looks like is we'll have d by dx, our differential, of the left-hand side expression, x squared plus 3x plus xy is equal to d by dx of the right-hand side expression, which of course is just 5. Okay, so the left-hand side is pretty straightforward to differentiate. This essentially, we can break this out individually. This becomes dx squared by dx plus d3x by dx plus dxy by dx. And this is all equal to d by dx of 5, which of course you already can see right away that this differential on the right-hand side is just going to be 0, since there is no x in the expression on the right-hand side. But we'll leave it as d by dx of 5 just for now. So, of course, the differential of x squared with respect to x is simply 2x, so we can compute that. And the differential of 3x with respect to x is just 3. And the differential of xy with respect to x, of course, this requires the product rule because we have two variables that are multiplied together. So we can break this out using the product rule. We'll first take the differential of x, and so we would write this as plus y, holding y constant, d of x by dx. Of course, you're going to see that that's just equal to 1, plus now holding x constant and taking the derivative with respect to y. And so this will just become dy by dx. And then this is, of course, all equal to the differential of 5 with respect to x, which is just equal to 0. And so now you can see that our dx by dx, this is just 1. And so we now have an expression where we have both the dependent function, y, and its derivative all embedded within the same expression. And so differentiating this implicitly is now just a matter of algebraic manipulation. And so we can say dy by dx, which using Newton notation is y prime, equal to negative 2x minus 3 minus y, all divided by x. And that's the result that we get when we differentiate implicitly. Okay, so let's now proceed to differentiate it explicitly. And so again, just as a reminder, our expression is x squared plus 3x plus xy is equal to 5. And in order to differentiate this explicitly, what that means is that we have to rewrite this equation such that it's in the form of y equals f of x. So we have to get y by itself. Again, that's pretty straightforward with this expression. It's just a matter of algebraic manipulation. And we can simply write this as y is equal to 5 minus x squared minus 3x, all divided by x. And now to differentiate this, we can make it a little bit easier for ourselves by writing each term individually. So this would be 5 over x minus 3. And so to take the derivative of this with respect to x, dy by dx, which is equal to y prime, is just equal to 5 over x, the differential of that with respect to x. It's the same as 5x to the minus 1. And so this becomes negative 5 over x squared minus the derivative of x with respect to x, which is just 1. And then the derivative of 3 with respect to x is, of course, 0. And so when we solve the derivative explicitly, we get this relationship that dy by dx is equal to negative 5 over x squared minus 1. And if we call this equation A and we call this equation B, at first glance it appears as though equation A does not equal equation B, which would be a surprise since we've taken the derivative, right? The left-hand side of the expression is saying that they should be equal. Y prime is equal to negative 2x minus 3 minus y over x for expression A. Likewise, y prime, the same y prime, is equal to negative 5 over x squared minus 1 for expression B. So in order to verify, and of course this statement of course is not true, the two are in fact equal, and we're going to show that right now, and this is what part C is. And so to verify this, what we do is we take this relationship for y prime, relationship B, along with this relationship for the expression for y, which we're going to go ahead and call relationship C. And so we substitute both B and C into A and basically show that these are equivalent to each other. Okay, so we're going to use expressions B and C substituted into A to show B and A are equal. Okay, so based on expression A, we have that dy by dx, I prefer Leibniz notation, is equal to negative 2x minus 3 minus y, so this is where we'll substitute expression C into A, where y is equal to 5 minus x squared minus 3x all over x. Okay, so now it's just a matter of algebra to show that dy by dx is equal to negative 2x squared minus 3x minus 5 minus x squared minus 3x. And so what we show is I had a mistake. So this is minus y. So I should have put some parentheses here. Minus y, which y is equal to 5 minus x squared minus 3x over x. And so when I translate that down here, this becomes plus 5, or excuse me, that remains a minus 5. So let me fix that real quickly. So this is minus 5, but this is plus x squared, and this is plus 3x. So you can see right away that minus 3x and plus 3x cancels. And then we have negative 2x squared plus x, so that leaves us with negative x squared. And so dy by dx becomes negative x squared minus 5 all over x. So now, if we take a look at our expression for b, recall that the expression for b is dy by dx is equal to negative 5 over x squared minus 1. And so this becomes negative 5 minus x squared. It's like I just realized I'd made another mistake. And so I'm actually, what I'm going to do is I'm just going to erase all of part C because this thing is riddled with mistakes. Okay, and so what we get, if we do this correctly now, is from part A, right? So from A, we have that dy by dx is equal to negative 2x minus 3 minus y all over x. And now we substitute our expression for, or C, our expression C into A. And so we get dy by dx is equal to negative 2x minus 3 minus y, which is minus 5 plus x squared plus 3x all over x. And then this is also all over x. Okay, so to do this, so at this point now it's just algebraic manipulation. And so to do this in a simple fashion, we'll first resolve the numerator. And so we have a common denominator of x among those three terms in the numerator. And so then this becomes negative 2x squared minus 3x minus 5 plus x squared plus 3x. And then this is all over x. And so again, our negative 3x cancels with our 3x. And so we then get negative x squared minus 5 divided by x divided by x. And then, of course, to resolve the denominator, we can just simply multiply this by 1 over x, 1 over x. And that then gives us that dy by dx is equal to negative x squared minus 5 over x squared, which is equal to negative 1 minus 5 over x squared. And that expression is the same as our expression that we wrote for b when we differentiated explicitly. So the technique works both ways.